you will notice that I changed the title from what is there. The title was from a paper, and this is from a thesis of Mark Bass, from the thesis that Mark Bass wrote, and it's very recent, and we are still working on some of the papers, so any comments and questions are very welcome. And it's in University of Southampton, and nice to be there. And my take on this EBEB is, hey babe, that's like in a Bayesian way. Anyway, so you see my title, and it's parameterization. I'm sorry that it's not motivated by an epidemiology or a clinical trial problem, but it's more statistical methodology and analysis that I would like to talk about. And it's parameterization, and I can bet almost 70–80% of you may not have understood hard what is parameterization is and what he is going to talk about. So I put up this slide. It is basically how we write down a model. For example, we could write down, observation Y is like a random effect U tilde plus epsilon. U tilde has a, random effect distribution, and epsilon has a random effect distribution. Alternatively, we could write it as Y equal to theta plus U plus epsilon, and the same distributions. So one parameterizations like for theta and U tilde and theta and U, one may look like an orange that, these are contour plots. One may show theta here, U there, or anyway. One may look like an orange, and the other may look like banana. I'm sorry about the resolution. This is green. I wanted to draw it yellow, but yellow I knew wouldn't come, but I drawn green, but it's hard to see from the back that this is a green banana-shaped contours. So where's the problem in this parameterization stuff is how the Gibbs sampler tries to explore this theta U tilde space or theta U space. It draws a sample there and then updates coordinate, the x coordinate there, and then update the y coordinate, so that is its second iteration. Then draws an x or theta and comes here, and then draws y coordinate, so comes there. So the Gibbs sampler is sort of randomly trying to explore whether there is an orange or banana, thus basically. But where the problem is, we don't know a priori what our space would look like. Would it be an orange or a banana? And that's what we are trying to understand in this thing. So with that, hopefully I've told you what's the problem that we are trying to do. Of course, the model will get complex and all that, and that's what I'm going to talk about. So that was the essence of, like, very, in simple terms, what my problem was. So I'm going to talk about there are three main parts of my talk. I'm going to talk about centered and non-centered parameterizations for linear models and do literature review. So this will be called the center parameterization. This number 1 would be called the center parameterization, and number 2 would be called non-central parameterization. I mean, both parameterizations are same. They give the same posterior distribution for theta. So they give you the same thing. And the second part of my talk is how does spatial correlation affect the convergence behavior of the parameterizations. I know there are a lot of people who work on spatial modeling, and spatial modeling is much more common. Just the last talk was on spatial modeling, and we had fMRI data, lots of spatial and spatiotemporal modeling. So we want to see what effect the correlation structure that we assume has effect on parameterization. What about the smoothness parameter in the Mattern family? Like how does that affect? Tapering is a new concept that was introduced in 2006. How tapering affects these parameterizations and non-stationarity, covariates, pattern of data points. So we want to learn we want to see how all of these affect the centered and non-centered parameterizations. And the third final part of my talk is what's in the abstract, and the title is we have a dynamically updated partial centering parameterizations, and will parameterization vary according to the pattern of the location of the data point. So so imagine a space, and we have a cluster of spatial points, and will we need to change parameterization as you travel through the space? So that's quite, I think that's the most exciting part, but I'm going to come back to that. So, and finish with discussion. So the first 2 points here is, I got started on this quite a long time ago. In fact, during my PhD thesis in Connecticut in 1990. So we have 2 papers on this topic that are well cited, like about 450 or so. So that's one in Biometrica and one in NASA. At that time, we didn't have spatial modeling. Spatial modeling was not, I mean, it was there, but on a different mode, not hierarchical Bayesian spatial modeling that we do nowadays. And then I had a paper with Gareth Roberts. This Roberts is the Roberts that he's going to finish up everything tomorrow. So he's right here. So you can ask him difficult questions as well. So we had a paper, we formalized, in this paper, we formalized a lot of the stuff that's there, and using rates of convergence and Markov chain Monte Carlo and all that, and that was quite exciting. And then I sort of left working in the area, and then there was a PhD thesis under Gareth Roberts' supervision by Omiros Papaspiliopoulos. Let me be racist, that's a hard to pronounce Greek name. I'm just going to call Omiros, although for scientific purposes I'll cite as Papaspiliopoulos. And they have lots of papers. These are two papers, the statistical science paper and this paper. They have other papers on the topic as well. So they looked at these parameterization issues, and I'm going to discuss about that as well. And then we have a PhD thesis by my student Mark. So we go back to Gelfand et al. So that's the simple example. So earlier I had just one random effect, but now I have n random effects, and these random effects are independent. There is no spatial correlation. So UI, so I'm repeating from my first slide, and then this theta UI, that parameterization, this is the uncentered or what we call uncentered or non-centered parameterizations. And if we just do the transformation, u tilde I equal to ui plus theta, then write down the model this way, yi equal to u tilde I plus epsilon I, that we call in those papers we call hierarchical centering or center parameterizations, that we coin the term there. The posterior distribution is same under both NCP or CP. So it doesn't matter. The posterior inference will not change, but the convergence will change quite a lot. And in fact, it is a very important problem because sometimes in one of the parameterizations you can't achieve convergence because the rate of convergence will be very close to 1, and I'll demonstrate that. I'll demonstrate that. So what in those PhD days, what we calculated correlations. We know correlations like those orange or banana that slows down convergence, and we calculated correlations, and on the basis of correlations that you can do the calculations, we got a dichotomous result that to reduce posterior correlation, adopt the centering parameterizations. If your random effect variance, this sigma square u, is bigger than the observation variance sigma square epsilon, and else adopt NCP. So hence CP is preferred, the centering is preferred if random effect variance is larger than error variance in the normal case. That is so this is in some sense signal to noise. If you have more signal for your random effect, then basically you will adopt the CP, and that's why we do modeling as well. But that's not the end of the story. So based on correlation, you can choose which parameterization to adopt. So we formalized, as I said before, we formalized in that Robertson Sahu paper basically. Suppose we got so this is a bit of fantasy land. So we are assuming the whole joint posterior distribution is multivariate normal with the mean mu and the covariance sigma, where the sigma inverse is partitioned this way. Then you can do the math, and basically what we saw, the rate of convergence of the Gibbs sampler is the maximum modulus eigenvalue of this guy, f equal to I minus LA inverse UA. I don't want you to memorize that formula. I'll do that for you. But so this is the rate of convergence. And what these rates of convergence, for quick convergence, we want these rates of convergence to be low, near 0. These rates of convergence, maximum modulus eigenvalues, so these are between 0 and 1. And so for lambda c, the rate of convergence for the center parametrization is sigma square epsilon over sigma square epsilon plus sigma square u, and for non-centered it's 1 minus lambda c. So you see the dichotomous behavior. If one is good, the other is bad, and so on. So convergence is faster when the rate is lower. So that's the point that we'd like to take from there. So generalizations, I mean, that's a simple model. We'll say, that my MSc student or my BSc student to do it. We had, Alan and ourselves and Brad Cullen, we did it for generalized linear model, GLM, and Omidas and Gareth and colleagues. They did for a broader class of hierarchical models. Gareth can tell me if I'm wrong. They defined NCP to be parameterization where the random effects you are independent of the global effects theta. The thetas are what you call the global effects, and also for heavier tail Cauchy double exponential Gaussian and exponential power distributions for the data model. They generalized all this, and heuristic remark is CP is better when data model has thicker tail than the random effect. That's from Gareth's paper. This is a point I'm not going to talk about. On these parameterization issues, there is something called interweaving algorithm. I'm not going to. So you do half CP and half NCP. I'm not going to talk about that at all. So I'll run away from there. So also from Omidas's thesis, very clever idea is to look at partially center parameterization or PCPs. So instead of writing as UI tilde is UI plus theta, instead of putting the whole theta in there, you put a portion like this. W is between 0 and 1. So W theta and parameterize that way. So and you can see if you put W equal to 0, then you get NCP, and if you put W equal to 1, you get CP. So think of CP and NCP as extremes of a class of continuous parameterizations and the continuous partially center parameterizations, and you can calculate the correlations, and actually you can set that correlation exactly equal to 0. Correlation between these random effects and the global effects to be exactly equal to 0 if you get this W to be like that. So that's a very clever idea. So that what that means, if there is no correlation, then we got the orange, and if we got the orange, we got immediate convergence. And that's so much easier. And correlation between UI and theta, and we'll return to discuss this dynamically updated PCP later. So this is my first sort of literature review. I would like to come to this part 2, like this parameterization for spatial models. So this is typical sort of model assumptions for modeling spatially point reference data. So you have a response, YS, and XS is a spatially varying covariate times global effect theta plus random spatial effect beta S plus epsilon S as nugget effect. People call it nugget effect or measurement error or microscale error or lots of things. So with data from n locations, Y equal to YS1 to YSN, we similarly define beta and beta tilde and epsilon. Epsilon S is the nugget effect. So covariance of epsilon. So covariance of epsilon, that is n by n. Call that C1, and beta S is Gaussian process. Covariance of beta is C2. So then writing X1 and X2 as design matrices, the CP, the center parameterization version would look like this. Y given beta tilde is normal X1 beta tilde C1, and beta tilde given theta is normal X2 theta C2. And by defining beta equal to beta tilde minus x2 theta, we get the NCP version, just as in 2. And I can show you what that 2 was. That 2 was that yi equal to u tilde I plus epsilon I, where u tilde I is ui plus theta. So just doing similar things, we get this NCP version which looks like that. So for both CP and NCP, assume the prior theta follows normal MC3. So C3 is another covariance matrix that we need to assume. So basically, we can use Linley and Smith, our friend Linley and Smith. That's the seminal paper, 1972 JRSSB paper. That we can use Linley and Smith to calculate these posteriors and conditional posteriors and these covariances as well. We can show that the covariance beta tilde theta is BC2 inverse x2 sigma theta given y. So this is the posterior covariance matrix of theta, the global effects given the data. And for covariance beta theta, it is BC2 inverse x2 minus x2 sigma theta given y. It will take some time to derive those, but these are effectively sort of those invariant correlations that I calculated before. So for the block updated gives sampler the rate of convergence, we can, from that Robertson-Sahu result, we can get this. That will be the max modulus eigenvalue of this matrix, and for NCP, it will be this matrix. That's an alphabetical soup. I'm not asking you to remember to take it to lunch, so leave that there. But that's why we'll explore how that behaves. And what we want to explore is, we want to change the correlation structure in C too. See what happens. We want to change the variance, like the signal to noise ratio in C1, and see what happens. And we want to introduce this tapering, blocking, and lots of fun in spatial statistics modeling that we do. That's what we would like to do here. So illustration of the rates, that's what we said we will do. So assume a simple model, y given beta no. So we just have a no covariates, very simple spatial effects, and that sigma naught is sigma naught square R naught. That R naught will have the spatial correlation structure, Mattern or exponential correlation structure that we would like to assume. Then we can calculate this lambda C and lambda NC. Again, we want these to be close to 0 if the parameterization is to converge faster. This doesn't still look like something we can analyze. But we can illustrate. How does R naught affect the rates? So assume, for the simplification, assume a flat prior on theta naught, like 1 over V naught. So this, so this V naught is here. That's in the prior for the global effects. That V naught is here. So that's the variance of the prior for the global effects. So assume a flat prior on theta naught, which we often do. We assume flat priors for the global effects, and we do the equicorrelation case. So this is still not spatial, but so all the random effects have equal correlation with each other. Then we can get these rates, like lambda C is sigma square epsilon over sigma square epsilon plus chi square, which depends on the rate of on the correlation rho, and we can get lambda C plus lambda NC equal to 1. Still that dichotomy holds. Still that one is, if one is better, the other is worse, and so on. So for rho equal to 0, we cover the rest for the independent random effects. I've seen that before. So we illustrated. I'm sorry about the color of the pictures here. So the first block of plots are for convergence rates for the center parameterization. So this is for center parameterizations, and this is for non-center parameterizations. And what you will see, I have summarized that. What you will see is that as rho, the correlation you assume in the model, correlation between the random effects, or n, the number of data points, that plays a role as well, increases, CP gets better while NCP gets worse. So CP gets better because all these rates are coming down. All these rates are coming down. So this is rho plotted here. So as you increase rho, the rates are coming down. So introducing more correlation is affecting you, is allowing you to converge faster. But on the other hand, if you, for NCP, which is this block here, if you introduce more correlation, they are getting worse. They are getting worse. And the in-between plots here, they are for different ends, And as you increase n, the convergence will be faster for, so as you increase n means you have a lot more random effects, or you have a lot more spatial location. And you can see what's the thing that Gareth told me a long time before. What you need to be careful, here the rates are about 1. This straight line here, if you can still figure out, they are about 1. So you may be in a very bad position, you may be in a very bad situation without you knowing it. That's what is the point that I'm going to talk. So how spatial correlation affects the rates? So we assume exponential correlation, keep Mattern for the time being. Assume exponential correlation, your correlation is e to the minus pi dij, and this pi is what we call the decay parameter. You can see, if you take phi to be large, if you can take phi to be large, correlation will be 0. D is distance, dij is distance between. So that there is a concept, effective range is basically when this correlation approximately equal to 0. But we can't have 0, so we approximate that to be 0.05, and then this effective range is 3/5. So beyond the effective range, 2 random variables will be uncorrelated. That's the interpretation. So define signal to noise ratio, delta naught is sigma naught square over sigma square epsilon. What these graphs show you, increasing effective range or spatial correlation and or signal to noise ratio, this, if you increase that sigma naught square over sigma square epsilon, weakens the convergence for the CP. You see these rates going down, and it slows the convergence for the NCP, the rates going up. So that's the picture. That's a clear picture that we see. So we basically numerically calculated the rates, the lambda C and lambda NC that I've shown. Again, we want smaller rates for quicker convergence. And so this is D naught. This is the effective range. As you increase the effective range, rates going down. As you increase the effective range, rates going up. That's for CP. That's for NCP. Okay, so this is tapering. That's my cartoon. What's tapering is, I would say a few words. What tapering is, the problem is with spatial modeling is that, two points may be far away, but with a spatial correlation like this, e to the minus pi dij, no matter how much dij is, this is never going to be 0. E to the minus pi something is never going to be 0. Okay, so you will have to deal with large, when n is large, you have to deal with large matrices, and which there is no sparsity. So what these tapering people did was like, basically, so you can say you want to taper and then cut off correlation after a certain distance. If you travel from a center to a certain distance, from any point where you are, you set your correlation to be 0. So from center to any point on the circumference, after that, you want to cut off correlation. But you need to taper. So that's why, this, without that big part here, the exponential is, the full model is like e to the minus pi dij, but you taper that, and basically you are cutting it off. Dij greater than d naught, the correlation will be 0. So that's tapering. And so which parameterization will converge faster with tapering? The more tapering you put in. Can you try to guess that? Which, the CP or NCP, which will converge faster? If you consider 2 cases. One is tapered at a certain d naught, at a certain distance, and one is not tapered. Sorry? Tapering is reducing correlation. It is reducing correlation from your model. It is cutting down. It is cut off at correlation. So tapering will be better for NCP. So we've drawn that. So convergence rates, so center parameterization, non-center parameterization. So conclusion here is same as above. Also, tapering increases the rates for CP. Increases means the CP gets worse. Increases the rates for CP and reduces the rates for NCP. It makes sense. The stronger the correlation, the better the rates for CP, and opposite is true for NCP. So tapering will, again, these are for different signal to noise ratio. There will be interaction with signal to noise ratio and so on. So it is there. So I think dashed lines for tapered and solid lines for non-tapered. So it's a little bit hard to understand, but tapering, because it reduces correlation, it will favor the NCP and so on. So at least we, okay, so how does the covariates influence the rates of convergence? We know the golden thing. When you have a covariate in an MCMC model, you center that to have zero correlation with the global, with the global interceptor. So this is center the covariates x to 0, always improves convergence. That you do all the time. Fix the variance components, for our study, and for independent random effects for CP, increase in the standard deviation results in decrease in convergence rates and vice versa. I don't have the graph, but I just have the results that I have sort of transferred. For CP, the increase in the standard deviation results in decrease in convergence rates. And for NCP, as SDX tends to infinity, the lambda NC tends to 1. As SDX tends to 0, lambda NC tends to 0 as well. So that's kind of again very strange, but easy to understand. As you increase the SDX, that's what the design people will tell you. Where you collect data, where you want to have lots of variability in your X so that you can understand more from the model. Then your CP will be better. But if you have more variability, then your NCP will be worse. So that's what is the result. It's quite fundamental. It's quite we were quite excited to characterize that, or excited to understand that. So we can think of, so this is for independent random effects, like that beta S's are independent. But if you assume a spatially varying covariates, then the results would be same story. Increasing correlation improves faster convergence for CP. So here we standardize the X's, take away the mean and standardize the X and see what happens, NCP. So, okay, so I thank God I didn't have the graphs for those, so I don't have explanations. So now we want to tackle the Mattern guy. That's an ugly formula. Again, don't remember for your tea or coffee. That's a Mattern formula, and there are two parameters. Basically, this phi, what you often call the decay parameter, and the nu, which is the smoothness parameter. And so popular spatial cases, nu equal to half, you get the exponential, nu equal to 1.5, you get this, tractable form, and for any half integer, you will get tractable form. And the last is, as nu goes to infinity, you get this Gaussian, what is known as the Gaussian correlation function. So define the effective range D naught, for which rho D naught phi nu equal to 0. Rho is that. So again, the effective range will depend on nu as well. This is not so, correlation function influence convergence. The result here is not so clear, but we find that worse rates for the Gaussian case for both CP and NCP. Here, you have to see the graphs here. Basically, the worst rates are for the Gaussian case, for this when nu goes to infinity case, and the better rates for exponential case. And here we didn't see that much dichotomy because maybe there are other things playing in there as well, and it's very nonlinear. There are other things playing into the behavior of convergence for both. So what happens if you do introduce geometric anisotropy? So geometric anisotropy, one cheap way to do that, instead of Dij, you put a affine transformation, and this is the distance vector, like Si ith location minus jth location, and then you can parameterize this anisotropy. And what that effect has, so you make one axis elongated. So there are two parameters, alpha and psi. There are two parameters. So axes are rotated anticlockwise through an angle psi and stretched in the direction of the x-axis by a factor of 1 over alpha greater than 0. That's how you can interpret. And you can see what's happening is, x-axis is stretched, a little bit rotated there. And so you can have all sorts of anisotropy that you can build in. And what happens then? Assume R naught, covariance. So the correlation phi dij star. Dij star is this, with the affine transformation, not H equal to identity there. And choose alpha, and so the result is similar. So we just did it for psi equal to 0, similar story. So convergence rate, again for CP up there and NCP, you can see the CP rates are going down as your effective range going up. This is 3 over pi naught, or these are effective ranges, as we said, but here they're going down. Anisotropy increases the rates for CP. NCP may not converge in certain cases because of these guys that you see the rates there. So all right, I'll forget about blocking. We can do similar studies, but let's come back to my sort of partially centered parameterization. So develop PCP for a general hierarchical spatial model. Choose the parameterization weights to remove the posterior correlation between the fixed and random effects. Study how these weights may vary spatially. Propose a dynamic update scheme when the variance components are unknown, and illustrate the results with a simulation and a real data example. That's quite a lot. So we have a general model here. So this is the intercept. This is the intercept process. YS, global effect plus intercept, and every covariate. So there is a slope. And the slopes are centered around a global effect theta k. So we can write down, crank it, all that, forget about it, it's too late to get all those details. And we can construct the PCPs we can manipulate these matrices, write down the PCPs, and the PCPs would look like this. And then we can optimize the PCP like set W equal to this, and then when the variance components are unknown, the exact convergence rate of CP 0 can be shown. So that's what we have, and to achieve this, beta W must be updated as one block and theta as another. So we want to see how does the PCP depend on correlation structure and all that. So we have a simple model again, so consider 200. So this is one simple example that, so we have 200 locations in the figure below. So these are the spatial locations where we have observed data. And obviously we did a clustering here. We did a clustering there, thinner and even thinner. So, and 3 effective ranges, root 2 over 3, 2 root 2 over 3, and root 2, an effective range of 0 imply independent random effects, return weights that are the same at each location, and patterned sampling location. So what happens? So then you see, so these are the interpolated surfaces of the weights. What's happening here is, you see, and there is quite a lot of information here. One is we are varying delta naught from 0.01, the signal to noise ratio from 0.01 to 100, and then we are doing A, B, C, referred to 3 values of the spatial correlation. A, lower spatial correlation, more spatial correlation, and more spatial correlation as you go down the column. What you can see here is, here the things are all in blues. All in blues means the weights are in blues means weights are almost 0. Here, you want to use the NCP for everything, everywhere. But if you vary the parameters, then you can see there we are mixing. We are in the middle colors. We are mixing. CP is getting more weights, and finally CP gets all the weights. Where this color is the W's are all ones. So this is the exciting bit. Like what region you are, where you are updating the random effects, you want to change your parameterization, and you may as well be somewhere there depending on where you are. So as the variance ratio increases, the weights increases to 1, as we had before. Increasing spatial correlation leads to increasing weights, and within each panel, areas of higher weights are concentrated around the areas of more densely positioned sampling locations. More densely positioned sampling locations are in the top left corner here, and areas of higher weights are more there. So you can see fader color, the blue is bottom there, fader color is there, and you can see that is happening as well. So we understood something from there. So let me skip this example. We did do a more bigger example, like we had only one process, now we had two processes, and so on. So now, a little bit about the dynamic updating. The optimal W, this ugly formula that is, vary with the parameters in C1 and C2. The optimal W varies in C1 and C2. Hence, when the covariance parameters are updated, W must be updated too. Will MCMC work? Still work for dynamically updated W? Yes, we have theoretical result that the Markov chain will still preserve stationarity if W is updated, and without going into theory, we illustrate with a practical example. So this is my practical example. So this is illustrate the performance of PCP and CP and NCP observations from 176 sites in within California. This is, believe it or not, this is a cartoon of map of California, and so these are the sampling locations. The measurements are at the annual fourth highest daily maximum 8-hour average. You must be saying I'm doing statistics. But there is a long history of using these statistics from the US Environmental Protection Agency. I'm not going into a lot more in there. One covariate is land use taking two values, rural or urban, including suburban is the only covariate. So you see 176 sampling sites. In California, we use 132 for modeling, the blues, and 44 validation, the reds. So model on the square root scale, inverse gamma 2-1 priors for variance components, that gives you a proper prior without getting into controversy like Gelman sort of stuff. We adopt the model with P equal to 2 processes, an intercept and a slope process. Remember, we have one covariate, so we have a slope process as well. Estimate the spatial decay parameters using a grid search. And we use the potential scale reduction factor from Gelman and Rubin, and its multivariate version, the PSRF M, to be the number of iterations required for the PSRF to fall below 1.1. And we also use a multivariate version of MPSRF as sync convergence of all the parameters. So these are acceptable, these are sort of well-known convergence diagnostics. So this is what happens to our weight matrices. Here the weights will be 2n by 2, and so what you can see here is that for the intercept, these are the two that we have summed up. So these are n by 2 matrices and we have done row sums, and you can see you need to vary the weights for PCP varies as you travel down the space, and it's not on. It will be surprising if you get all on one color, all either blue or the top red. But here, the weights, you need to vary the weights. And the similar story sort of, you will see that higher weights will be where you have more cluster of the points and so on. So we have some of these statistics and the effective sample size, ESS. So for theta naught, theta 1, so we have two parameters, one global intercept, global slope, and the two variance components. One variance component for the spatial intercept process, one for the slope process, and one for the sigma square epsilon. And you can see, so PCP and MPSRF, and ESS per second, this is effective sample size, and this is effective sample size per second. So MPS, here the NCP is losing out, and CP will win. CP will win. Its MPSRF is a lot lower. So PCP has better ESS for the linear parameters. However, CP has a shorter runtime, hence wins over PCP in ESS per second. Why that is so? Because we have to, in PCP, you have to calculate the weights. So that's why it slows down per second shorter, because CP has shorter runtime, that's why, and NCP is much worse than the other two. NCP is much worse than the other two. So that brings us to the discussion. Just one slide. So investigated the effect of spatial correlation on MCMC convergence for different parameterizations. CP is preferred when there is higher levels of spatial correlation or higher signal to noise ratio. I had lots of examples and cartoons and picture. Proposed spatially varying PCP for spatially varying coefficient models that for these normal hierarchical models, and we've seen what's the effect of that. PCP can converge immediately as we have done. Centering is also preferred in areas of higher concentration of sampling size. We have seen that. proposed a dynamically updated version of PCP that we guaranteed will converge. And what I didn't talk about, there is another chapter to this, is extended these to the non-normal 2-bit models, non-normal 2-bit models, but that will be another day. So with that, I would like to stop and thanks for listening.
Thank you. So we do have time for questions.
Sujit, very nice. So the interweaved, you said you wouldn't talk about it, but I mean, it's obviously for many of the models you're talking about a natural competitor, and you can sort of see how it might overcome some of the disadvantages of the PCP. It seems to be the PCP's main advantage, as far as I can see, is that it has more flexibility over the interweaved, and that you can do it in a multivariate way. You can non-center different types of the model in different proportions, and I don't see the interweave necessarily has analogs that extend to that. Do you have any thoughts about that?
No, we didn't think much of that. Our main thing that went was in that California example where we experimented with the PCP, but you're asking, could we do more for multivariate? Maybe this YSS will be multivariate. Yes, I think that will be something definitely more interesting to do. The interweaving, the main problem is we can't show that it will converge immediately. So it may be something good, something bad. But here, at least for PCP, we can, of course, we can compare in practical examples, calculating the MPSRF or this ESS, but we haven't explored that interweaving. Maybe that's an interesting idea. And do this for multivariate is interesting as well, but it needs bodies.
Okay. Any other questions? Okay, since it's time for lunch, let's thank again both speakers and conclude. Yeah.